Okay, so last chapter we talked about ionic compounds and how they're formed when individual atoms gain and lose electrons, and that makes them ions, and ions are just attracted to one another. They're held together just by that positive and negative charge that makes them attractive. That's what characterizes ionic compounds. And this works because metals have very low ionization energies. It's really easy to get rid of electrons. And nonmetals tend to have high electron affinities, which means it's easy to give them electrons. But in this chapter, we're going to talk about a new kind of bonding called covalent bonding. And covalent bonding occurs between two atoms, which are nonmetals. This is how you're going to know what kind of a compound it is. Two nonmetals make covalent bonds and therefore covalent type compounds. If you have a metal in your structure anywhere, then chances are you have an ionic bond and an ionic type compound. But nonmetals, as we know, they all want more electrons. So if I put two nonmetals together, then they're not going to give away electrons like they did when you had a metal and a nonmetal. There's going to be no exchange of electrons. That's why you can't have ions. So instead, what they're going to do is, to get as many electrons as they want, is to share their electrons, to say, hey, look, you have one, you want another, I have one, I want another. Why don't we move in together so that my electron is occupying your space, you can feel like you own it, and your electron is occupying my space and I can feel like I own it, and then we'll both feel like we own two electrons instead of just one, for instance. So the Lewis dot structure is basically a way of representing the sharing of the electrons that we have that go on between two nonmetals. And so, for instance, I can draw simple Lewis dot structures for individual atoms and elements, like lithium is in group 1, so it has one electron in its valence shell, so I put a little dot there. And beryllium is in group 2, so I can put 2 electrons in its valence shell, so I'll put 2 dots there. Boron's in group 3, so I'll put 3 dots because it has 3 electrons in its valence shell. You guys are all, you can all predict how many valence electrons a neutral atom has, right? You can still do that? I sure hope. Carbon has 4, so we would put 4 dots around it. And they're almost always unpaired just to start. And then we start pairing them up. So nitrogen has 5, 1, 2, 3, 4, 5. And it doesn't matter which side gets the 2 and which other sides get the 1 individuals, right? I could have put this 1 electron on the other side of lithium. It doesn't really matter. I'm just trying to show that lithium has 1, and it doesn't matter which side of lithium I put it on. I'm trying to show that nitrogen has 5, and it doesn't really matter which side gets 2 electrons or which side gets 1 electron. Oxygen has 6, so 1, 2, 3, 4, 5, 6. Does this make sense? In fact, I think you guys might have had to do this for this last homework assignment. I'm not sure. Chlorine has 7, 4, 5, 6, 7. You guys think you all can all do this? Neon has 8. 4, 5, 6, 7, 8. Helium's the only one that's got 2 that are paired rather than unpaired, and it's because they're stuck in the same shell. So that's actually your first in-class activity sheet exercise. You guys can do it. So for carbon, tell how many valence electrons it has. For instance, it has 4 valence electrons. Give the electron dot symbol for the neutral element. Okay, here's carbon with 1, 2, 3, 4. And then this is just to kind of remind you, you can't forget about the fact that, sometimes they also form ions. This would make a plus or minus 4 ion. Everybody think they can do section 1? Feel pretty confident with that? Okay. Excellent. All right. Well, then let's look at putting these together in bonds, all right? That's not what I meant to do. Here we go. So just like we were looking at with ionic compounds, when we make covalent compounds with covalent bonds, we still want full shells. That is to say that we still want 8 electrons, unless we're hydrogen and we just want maybe 2 electrons. So what we see then, we have one hydrogen atom with 1 electron, and he encounters another hydrogen atom with 1 electron. I'll draw this one as a circle instead of a dot. And hydrogen thinks, gosh, it'd be nice to have 2 because then I would be just like helium. Helium's the closest noble gas. That would be awesome. But I only have 1, and if I encounter another hydrogen, that's where they say, hey, look, I can share mine with you, you share yours with me, and in the end, there will be, we can each see 2 electrons. So we can each feel like we have a full shell, just like helium, and that is going to make us happy. Everybody see what they did there? Sharing electrons. So at its simplest, we can look at Lewis dot structures as a kind of a puzzle where we fit together pieces such that we end up with a full shell on all of our pieces. So let's look at, for instance, fluorine here. Fluorine has 7 electrons, 5, 6, 7. And if I encounter another fluorine that has 7, and I'm only showing these as dots and circles so that hopefully you can see which electrons came from who. And fluorine is next to neon, wants 8, just like neon, it only has 7, but if this fluorine shares with that fluorine and this fluorine shares with that fluorine, then they can each feel like they can see 8 electrons. You can each feel kind of like they own 8 electrons because they're sharing. Maybe it would be easier if I did this with different colors. But are you guys following me so far? Sharing electrons so that we get a full shell, which is usually 8. That's the octet rule. So that works really well with, say, 2 hydrogens and 2 fluorines. It'll also work really well if I have, say, 1 hydrogen and 1 fluorine. 1 hydrogen, look, I'll do a different color. That might help. 1 fluorine. Hydrogen wants 1 more, so it can have 2. Fluorine wants 1 more, so that it can have 8. So if we put these together, we can end up with a hydrogen fluorine molecule. I should have done some black here. One of those electrons coming from the hydrogen, 1 from the fluorine. Okay, so it's just a little bit of a puzzle. Okay, I've got a hole here, got a hole here. So this one can fill that hole and vice versa, and then they'll stick together and make a bond. We can also represent each of these. Those 2 electrons can be represented by a single line. That single line means 2 electrons, like 1 on each side here. But sometimes people do use individual dots on a side. They use bars instead of lines. So we can, if that makes it kind of clearer to see, we can draw it with, like that with this line. That one line means 1 bond, 1 single bond between the 2 atoms, and it constitutes 2 electrons. So we can check this molecule pretty quickly and say, okay, yes, this hydrogen appears to own 2 electrons, so it's happy. And this fluorine appears to own 8 electrons, so it's happy. And then we can be confident that this is a valid structure for a valid compound. Okay. Let's do one more. It's just a little bit bigger. We can do one here with nitrogen, which has 5 valence electrons. And if I make a compound between nitrogen and hydrogen, There we go. You can probably see that I can form a bond here, but nitrogen still wouldn't be happy. In order for nitrogen to be happy, I would have to form 3 bonds with 3 different hydrogen atoms. And that totally happens. That's the right formula. Nitrogen reacts with hydrogen to make the formula NH3. And so when we draw the Lewis dot structure for that, we can say we have 3 bonds to hydrogen, each of those lines representing 2 electrons. And we could say that one of each of those electrons came from hydrogen, and the other electron in that bond came from the nitrogen. Okay. And what you'll often see is that things in group 5, which have 5 valence electrons, then will make 3 bonds to give it a total of 8 valence electrons. Things in group 7, which have 7 valence electrons, will generally make 1 bond so that they will have 8 valence electrons. Can you guess, say for oxygen, which is in group 6, everything in group 6, how many bonds will oxygen typically make so that it has 8 valence electrons? Perfect, right on. Okay, so if we go over to our chapter, this is 5.1, but it's chapter 4 in your 7th edition text, right? So don't let that bother you. Part 2, we're drawing Lewis dot structures by first drawing the symbols for each element and then putting them together. So exactly like I was doing here. I would first draw each element and then I would put them together. I first drew each element, put them together. That's what I want you to do. Here's each element, then I put them together. That's what I want you to do with this section, section 2. Everybody feel like you can do that, kind of play around with it? It's like putting together Legos or puzzle pieces, however many is going to fit there. You guys want me to do 1 or 2, or do you feel comfortable with this section? Okay, let's see. I will do H2O. So we're going to see we have an H and another H. We have an O. How many electrons does oxygen have? Valence electrons? 6, perfect. Okay, so 1, 2, 3, 4, 5, 6. Okay, can you guys see if I could have picked up one of these pieces? No, it's not gonna let me do it that way. I picked one up and kind of moved it around, how I could manage to put this together so that the oxygen has 8 and each hydrogen has 2. Look at that. Where should I put those hydrogen atoms so that they fill the shells on oxygen? Megan is exactly right, either side of the oxygen. So this side only has 1 electron and I've got a hole. This side only has 1 electron and I have a hole. I've got 2 on the top and 2 on the bottom. So if I use that hydrogen to plug that hole and that hydrogen to plug that hole, then it's going to look something like this. Fill the shell is another way of saying I want to have 8 electrons around oxygen because 8 gives me a full shell. Remember the electrons that the electrons surrounding the oxygen, electrons surrounding any atom fill my shells, level 1 shell, the S subshell gets 2 electrons, 2 shell, S subshell gets 2 electrons, 2 shell, P subshell gets 4 electrons. This is oxygen, which comes into the game with 8 electrons total and only 6 in its outermost, which in this case is level 2, valence shell. So if it can get 2 more electrons to dump into the P subshell, it will have a full level 2 shell, which is why it makes a 2- charge if it forms an ion. But if it can't form an ion, here's another way for it to get it. It can take these electrons from hydrogen and make it feel like it's filling that space, even though it's sharing instead of just taking. Okay, so that's what I mean by fill the shell. I want, and really you don't have to be able to do this. Remember, I'm not testing you on electron configurations, although I wanted you to know what they were for exactly this reason, so you could figure out why it was doing what it was doing. But the shortcut is just to say, it wants 8. It has 6. How do I get 8? Oh, if I just share 2 more with it from 2 other atoms, then I'll have 8. So that's the octet rule, is the rule of 8. 8 electrons gives it a quote unquote full shell, unless you're hydrogen, which in case it's a rule of 2. You with me here, Denny? Diana? I'm not going to use more than 8. For the purposes of this class, we're not going to ever exceed the octet rule. So oxygen wants 8. It doesn't want more than 8. I can do the first one. Cl2, it looks just like the F2 I did on. So Cl has how many valence electrons? Valence electrons. 7. It has 7 because it's in group 7. So here's chlorine with 1, 2, 3, 4, 5, 6, 7. And here's another chlorine with 1, 2, 3, 4, 5, 6, 7. They each want 8. They each own 7. What can we do? Might be easier if I put my extra electron on the top. There we go. Is that easier to see? What will I do with my 2 chlorine atoms? Fill the empty spaces. That's exactly right. I have 7 and I want 8. So there's this empty space for the 8th that I would like to get. I have 7 and I want 8. There's this kind of hole for this 8th that I want to get. So if this guy comes in and fills his space and this guy comes in and fills his space, then what we see is we get a bond between the chlorines. They're each sharing 1 of the 7. So they each have 6 that are not shared. We call these unshared electrons or lone pairs because they're alone on the atom. That makes sense. So then each chlorine atom, the one on the left, feels like it has 8. That makes a full shell, just like the closest noble gas. The chlorine on the right feels like it has 8. That makes a full shell, just like the closest noble gas. They've each contributed 1 of the 7 so that they can enter into this relationship where they both feel happy and satisfied with 8. Okay. Might be kind of hard to see the empty spaces, but the empty spaces are basically anywhere where you don't have 2, where you don't have a pair. It's convenient that if we look at these as little blocks and we put 2 on each side, then there's 8. So anywhere where you don't have 2 on each side, that's going to be an empty spot. That's going to be an empty space. Okay. I will do one more but I think that you guys can do these if you just sit down and practice. So carbon has four electrons. And then I have 4 hydrogen atoms, and they each have 1 electron. What am I going to do so that that carbon can have 8 and that each hydrogen can have 2? Yeah, you guys are exactly right. Carbon has here 4 empty spaces. Here, I'll put them in blue. There's an empty spot here, because there should be 2 on each side. Empty spot here, empty spot here, empty spot here. So if each of my hydrogen atoms comes in and takes one of these empty spaces, then they will all be full, and then I will have 1 hydrogen on each side of the carbon atom. Okay, so now carbon feels like it has 8. You can count 8 there in those 4 single bonds. That's a full shell. And each hydrogen feels like it has 2. That's how many it sees. That's a full shell for hydrogen. That's the level 1 shell. You guys following me here? Okay, it takes a little practice. That's why I give you guys these in-class activity sheets, because I want you to practice, because in the doing of it is where you're going to learn it. So for sure, do this section before you come to class on Wednesday. Okay, these are simple Lewis dot structures, single bonds only. We see just as many bonds as we expect. Carbon came in with 4 electrons, it wants 8, so it's going to make 4 bonds with the 4 electrons it has. Carbon comes in with 6 electrons and it wants 8, so it's only going to make 2 bonds with its 2 unpaired electrons here. But there are some more complex Lewis dot structures that kind of surprise us in the way that they end up being put together. And so this method is just fine for simple structures where we're kind of puzzly putting them together. But there's another method that I want you to know and memorize that will get you the right answer every time. This warmer method is probably good 65 to 80% of the time. But if you want to be right all the time, then there is a method to follow. There's strict rules, and if you just follow them, you'll always get it right. Maybe that makes you feel better that there's a method rather than just eyeballing it. I don't know. But let's try this. So for more complex Lewis dot structures, there's 5 steps to follow. So for number 1, so steps for complex, and not just complex Lewis dot structures, you can use these for all structures, simple ones too, but you're going to need to do them for the more complex ones. All right, so step number 1, we're going to count the total number of valence electrons available. We're basically saying, all right, every atom that's in this molecule, how many valence electrons do you have? I'm going to count them and then reassign them. But first I have to see how many I have to kind of play with. You know how to tell how many valence electrons an atom has. You just look at the column. And you were able to do that on the first exam too. Okay, step 2, we're going to start building the structure kind of from the inside out. So we need to arrange the atoms in the way that they are connected. I'm going to say in order of connectivity, just how they're connected to one another. And there is a shortcut for this. Here's the rule. That is, the first atom listed is in the middle. Unless it's hydrogen. Hydrogen can't be in the middle of anything. If hydrogen is listed first, then you're going to look at the next atom listed. So you're going to arrange them by how they're connected. And step 3, we're going to connect these atoms that we just arranged with single bonds. That is, the central atom will have a single bond to each exterior atom. If they're not bonded together, then they're not part of the compound. So it's important that they each have at least one bond to the middle. So that's just 2 shared electrons here. So we connect the central atom with a single bond to each exterior atom. And as we're doing this, we might track how many electrons we have left, because we only have the number of valence electrons that we started with in order to try to fill these connections. So we'll track those. In step 4, any remaining electrons that you have after you have already connected your atoms with single bonds, we're going to distribute in the following manner. Distribute remaining electrons like so. In the following order. Step 1, we're going to fill the shells for every exterior atom. Exterior atoms first. So add electrons to each exterior atom. You should have enough to fill all of those. To fill. So 8 for almost everything, or 2 if I'm hydrogen. That's the full shell. And then if you have any remaining electrons after that, and you won't always, but sometimes you will, if you have any remaining electrons after you've already filled the exterior shells, then we can add any remaining electrons to the central atom. All right, that's 4 steps. There's one more step. We should be done, but sometimes we're not. Sometimes this is just not enough to distribute the electrons in this way. Not everybody gets a full shell. So step 5 says we're going to evaluate the structure. If when we evaluate the structure, we find that everybody has a full shell, then we know we're done. Everybody has a full shell. We've used all the electrons available, and we can say the structure is correct. But if they don't have a full shell, then we're going to share more electrons than just the single bond. So if necessary, share more electrons from the exterior atoms. I can't add more electrons because I've used all of the electrons that are available, but I can take one of the lone pairs from an exterior atom and move it into a bond to the central atom so that it gets a full shell. Okay, so here are my steps, and I'm going to do 3 examples for you to show how this works and what kind of structures that you can see. What do I mean by kind of more complex? Mostly just being able to predict double and triple bonds, or if something is making more bonds or fewer bonds than it normally does, then this will definitely get you there every time. Okay, so, but I'm running out of space here, so I might have to move away from this list. So I hope you guys have all had it written down. Everybody has this written down? Okay. Good. So you can follow along. as I do a couple examples here. So the 3 examples I'm going to do just right here are I'm going to do a polyatomic ion. I know you guys have been waiting all week to find out what the heck polyatomic ions are made out of. I'm going to do sulfur dioxide and I'm going to do carbon monoxide. All of these are structures that do exist in real life and that kind of violate the rules that we would expect. Okay, so NH4 plus. Rule number 1, count total number of valence electrons. How many valence electrons does nitrogen come to the game with? Just look at the periodic table. Perfect, nitrogen comes in with 5. How many valence electrons does each hydrogen atom come to the game with? Perfect, each hydrogen atom comes to the game with 1, and there are 4 hydrogen atoms that are coming to this game. All right, now this tells us something else very interesting. What does a positive charge mean? It lost an electron. Perfect. I'm missing 1 electron because I have a positive charge overall. So in my total number of valence electrons, I have lost 1, and I've got to count that. My total number of electrons available for distribution. So 5 plus 4 times 1 minus 1 gives me how many total electrons can I play with in the structure? 8. Perfect. All right, and now we are going to distribute them as we see fit. So that was step 1, was just counting. And if you count correctly, then the rest of this should work just fine. If you find that it's not working, you might go back and count again and make sure that you counted correctly. All right, so step 2 says we're going to arrange the atoms with the first atom listed in the middle and the other atoms listed all on the outside. Okay, so nitrogen's in the middle, and I have 4 hydrogens, so they're all on the outside of that first atom listed, which is central. So that's step 2. Everybody with me? Just get an idea of where these atoms are. And then step 3 says we're going to make a single bond between the central atom and each of those exterior atoms. Because if I don't have a bond, it's not a part of my compound. Okay, so that is step 3. Everybody with me on step 2 and 3? Don't want to continue until... Okay. Now that I finished step 3, step 4 has me distribute remaining electrons, but I need to know how many electrons remain. So, how many electrons have I used while I have put in these single bonds? Jay Houston says 8. Does anybody agree with him? Okay, good. Okay, it's an even 8 because I have 4 bonds and each bond represents 2 electrons, right? If that helps us, we can emphasize this. So I've used 8 electrons. How many did I have to start? I had 8. Okay, so let's say I had 8, I've used 8. How many do I have left? None. 0. Okay, I hope you guys can do this kind of math because you can't use a calculator on this upcoming exam. Is that okay with you? This kind of 5 plus 4 times 1, what you can do this. You can do 8 minus 8. Yeah, you can, I think you can do this kind of math. Perfect. Okay, so step 4, we're out of electrons. We'll skip step 4 because we don't have any more to distribute. And then we move on to step 5, which says evaluate. So now we're going to evaluate step 5. Does this structure fill the octet rule or fill the shell for every atom in it? Is everybody happy? Yeah, the nitrogen sees 8. So this is what the nitrogen sees. This is why we share. There's 8. Hooray! And each hydrogen sees 2. That's what each hydrogen sees 2, and that's full for hydrogen. Hooray! So we're done. We can feel confident that this is the right structure. And here's one more thing we do for polyatomic ions often, and this is just to remind people that it is an ion. We'll put it in brackets and say, hey, this thing has a charge overall, by the way. But that's not as important. What I really want you to get is this structure in the middle. And by the way, this structure is really interesting. Nitrogen usually has 5 valence electrons, but usually makes 3 bonds. So some of you might be looking at this saying, what the? Nitrogen only ever makes 3 bonds. That must be wrong. But this is the right structure. It's the only way we can distribute 4 hydrogens around that nitrogen and get a full shell with as many electrons as we have. Okay, so this is kind of an exception to what we would expect to see because nitrogen is making more bonds than we usually see. And yes, Megan, we only mark charges if there's a polyatomic ion. Everybody feel pretty comfortable with the NH4 plus before I move on to SO2? I have 1 vote for moving on. All right, good. Let's try SO2. Okay, step 1, count valence electrons. How many electrons does sulfur come in with? 6, beautiful. And I have 2 oxygen atoms, and they each come in with how many electrons? 6, careful, 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 careful. Group 6 has 6. So I have a total of how many valence electrons? How many electrons can I play around with here? 18, perfect. Again, you guys won't have a calculator, so I hope you guys can do that. And again, if the structure's not making sense, then go back and count again. That's not a common mistake, but it's common enough that it doesn't hurt to check. Okay, 18 valence electrons. Step 2 says, I'm going to arrange these in the way that they are connected, and the first atom listed is central unless it's a hydrogen. In this case, it's not a hydrogen, so the sulfur is in the middle, and it's connected to 2 different oxygen atoms. So that's step 2. And step 3 says, I better make sure that I've got at least a single bond there so that they're all part of this molecule. That's steps 2 and 3. Everybody with me so far? Okay. How many electrons have we used? And therefore, how many remain? We've used 4 because we have 2 single bonds and each bond represents 2. Excellent. Okay, so we've used 4. And so how many remain? 18 minus 4. Shay Houston, you're going to have to watch your math on this exam. I'm sorry. Okay, we have 14 left. So now we move on to step 4. It says just distribute the remaining electrons, and we have 14 remaining. And we're going to first, this is very important, always, 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 you have to add them to the exterior atoms first. So 14 electrons around exterior atoms until I have full shell. So 1, 2, 3, 4, 5, 6. This oxygen already had 2. So I only need 6 around this oxygen atom to give it a full shell. Does everybody understand that? Following me here? So on the left-hand side, this oxygen atom has 2. How many more electrons does it need to have a full shell? It has 2, and it's going to need 6. Again, just like the one on the right, because 2 plus 6 is going to give it a full shell of 8. It came in with, yeah. All right. So how many have I used? I have filled both shells for my oxygen atoms, my exterior atoms. How many? Like, be perfect. I've used 12 because I put 6 on the right and 6 on the left. So if I had 14 left and I've used 12, then Megan is exactly right, anticipating my next question. I have 2 electrons remaining. So for step 4, part B, it says add any remaining electrons to the interior atom. So that's where those 2 electrons go. And I can say, good, I'm out of electrons. Awesome, I have distributed all that I have. So I can move on to step 5, and step 5 says, evaluate the structure. Do all atoms have a full shell? Is everybody happy? You guys tell me. Uh-oh, Megan says no. What's wrong? Sulfur. What about it? It needs more. How many does it have? It's missing 2. It doesn't have 8. It only has 6. Okay, so in order for sulfur to be happy, it needs 8. In order for it to have a full shell, it must fit the octet rule. It must have 8. It only has 6. So what I'm going to do then is take 2 electrons from one of my oxygen atoms. And I'm going to move these 2 electrons over to the space in between the sulfur and the oxygen. So this oxygen is sharing those electrons. And actually, it doesn't matter whether I do it from the oxygen on the left or the oxygen on the right. They're identical. Okay. You guys tell me, which oxygen atom do you want me to use to share more electrons from? The left. Okay, so I'm going to take, let's say, these 2 electrons, and I'm going to move them in here. So I'm going to erase the electrons from that spot. And I'm going to put them now in between the oxygen and the sulfur. Okay. Notice how I didn't add any more electrons than I already had. I can't. I'm out of electrons. I just moved electrons that were already distributed to a different location. Okay. Now that I'm sharing 2 extra electrons, I have to evaluate again, stepwise, one set at a time. Is the structure happy now? Is that good? Diana says yes. Anybody else agree? Perfect. So we see then that the oxygen atom on the left appears to have 8 electrons, so it's happy. The sulfur atom in the middle appears to have 8 electrons, so it's happy. And the oxygen atom on the right appears to have 8 electrons, so it's happy, and everybody's happy. And don't let it bother you that one of these has to share 2, one of these has to share 1. This is one structure of several that we could draw the double bond on the right-hand side. That double bond is actually kind of distributed between the 2, but we're just taking the snapshot in time and saying, okay, we've got, for the Lewis dot structure, 1 double bond, 1 single bond on that sulfur, and 1 lone pair. Note here, this oxygen is making 2 bonds, which is what we normally expect to see for oxygen, which comes in with 6 electrons. This oxygen atom's only making 1 bond, so that's a little bit fewer than we'd expect. Sulfur here is making 3 bonds, and since it comes in with 6 electrons, we normally expect it to make just 2 bonds. So that's why I gave this as a particular example of a more complex Lewis dot structure, because it's not fitting maybe our preconceived notion of how many bonds these atoms should be making. Okay, but this is the right structure. It's the only way we can put 1 sulfur atom and 2 oxygen atoms together to get 18 electrons, okay, so that everybody's happy. All right, any questions on SO2 before we move on here? Okay, I hope you guys are seeing that when you follow the rules up here, when you follow the rules, then the structure builds itself. And you don't have to second guess, you're just following the rules and you'll get there. All right, let's try this. Carbon monoxide. Carbon comes in with how many? 4. Perfect. Oxygen comes in with how many? 6. So how many total electrons do I have to share here? 10. Excellent. That's step 1. Step 2, put these, let's see, arrange them. Carbon is central because it's listed first. There's only one oxygen, so there we go. Step 3, got to have at least a single bond. That's step 3. Now, step 4, distribute remaining electrons. How many electrons do I have left over? How many remaining electrons are there? There are 8. I have used 2 in this single bond, so now there are just 8. Okay, so part A, where do I put the electrons first? On the exterior atom, in this case the oxygen because it was listed second. Perfect. How many more electrons does this oxygen need so that it has a full shell? 6. It already has 2 by virtue of that bond. Perfect. So now we need 1, 2, 3, 4, 5, 6. And that has a full shell. So that was part 4A. Now, how many electrons remain for step 4B? 2. And 4B says I'm going to put those 2 electrons where? On the interior atom, which in this case is carbon because it was the one listed first. Excellent. Okay, now I'm out of electrons. So we move on to step 5. Step 5 says evaluate. What do you guys think? Does everybody have a full shell? No, C is not full. Okay, what do we need? How many more electrons does carbon need, does it look like? Okay, well, it needs some more. So what I'm going to do is I'm going to take, what will you tell me? What do we do if we don't have enough? What do the rules say? Share electrons from exterior atoms. Oh, look, it's even right here. If necessary, share more electrons from exterior atoms. Okay, so I'm not going to say, oh, let's share these ones because carbon's the central atom. Okay, not going to do that. I'm going to come from the oxygen because it's the exterior. So I'm going to move those electrons in. Hang on a second. We'll do one step at a time. It's always a good idea to do just one step at a time, and then that way we never overdo it. Okay, so I've shared electrons, and before I do anything else, I'm going to evaluate it again. Is everybody happy? No, who's not happy? Carbon still needs 2 more. Okay, so I'm going to, Jay Houston and Diana were exactly right, but I just wanted to do this kind of stepwise. We're going to move these 2 electrons in to the middle. Again, we're sharing from the exterior atom. So they're not going to be there anymore. They're going to be there. Okay, now that we've shared 2 more, we evaluate again. Does everybody have a full shell? Hooray! Okay, so the carbon atom on the left appears to own 8 electrons. And the oxygen atom on the right appears to own 8 electrons. So both atoms are happy. So this is the correct structure for carbon monoxide. Danny, okay, so this is a really good question. Here we used single bonds. That is just one bond. Here we used a single bond, and we call this a double bond because it has 2 bonds occupying the same space. This is a triple bond because it has 3 bonds occupying the same space. As it turns out, for the purposes of this class, you can only ever have up to a triple bond. You can only have 3 between any two atoms. Can never have more than 3. So we'll never see a quadruple bond in this class, for instance. So good question, only up to triple. Really good question. Note here, carbon usually comes in with 4, so we usually expect carbon to make 4 bonds. Since oxygen comes in with 6, we usually expect it to make 2 bonds. And here now neither of these atoms is making as many bonds as we might expect. But this is the only way I can get carbon and oxygen to distribute as many electrons as they have and have everybody with a full shell. So we know that that's the right structure because we followed the rules. We got it. Any questions on these? Okay, so if we look at our ICA sheet 5 number 1, part 3 has you drawing more Lewis dot structures. And for these ones, I think you'll find it easier to use the rules step by step wise. And I've given you a lot of structures to practice here because as you practice them, then the rules will become kind of second nature and you'll get better and better at them. So lots of practice on these Lewis structures. And do you guys want me to do one more, or do you feel like you can follow that process? You feel good? Do you want me to do an example, another one of these? Do the hardest one. I don't know which one's the hardest one. You know, I'll do this one. Because for this series, the C2H2, C2H4, you're going to say, what's in the middle? So this might be helpful. Okay, so for C2H4, well, hang on a second. I'm not sure what question you're asking, Danny. There will be 6 hydrogens in this compound, yes, if that's what you're asking. But let's look at this one. How many valence electrons does carbon come in with? 2 carbon atoms. They each come in with 4, good. And I have 4 hydrogen atoms, and they each come in with how many? So how many total electrons do I have? 12. Perfect. Okay, now I have 2 carbon atoms, so we're going to say these are both central. This is the center of my molecule. And then my 4 hydrogen atoms are distributed around them. And you'll find that it ends up easier if we're just going to make this nice and symmetrical. And that's step 2. Step 3 says, let's connect everything with single bonds. So now we have a single bond between my 2 central atoms and then single bond between my central atoms and my exterior atoms. Everybody feel pretty good about steps 2 and 3 for this one? Okay. How many electrons have I used so far? And so how many more do I have left over? I have 2. Sorry, I've used 10. I've got 2 left over. Okay, so step 4a says let's put these electrons on exterior atoms. Which exterior atom should we put these 2 electrons on? Diane's exactly right. None of them. They're all hydrogen atoms. They're all full. So step 4b says, where do we stick them? On the central atom. And here I have 2 carbon atoms, so it doesn't matter which one I pick, but I could say put them on that one. Okay. Now step 5 says evaluate the structure. What do I see? Everybody happy? No, who's not happy? Yeah, this first carbon on the left-hand side only has 6. So what if I take those 2 electrons and I put them as a double bond? Everybody happy now? That's it. You guys can do this. Everyone is happy. Everyone has a full shell. You guys can do this. It does take time to follow the process carefully. You guys have plenty of time on your exams to be careful. And that's what I'm recommending, is just follow the rules. Don't take shortcuts. Don't just assume that you know, but just step by step, go through the process and you'll get it right. All right. Nope, you have to memorize the rules. I'm not going to give you the rules on the test. You'll have to know those. Good question, though. Good question. Okay, last thing we have to talk about Lewis dot structures before we continue is just a little preview for organic chemistry. We're going to talk about condensed structures and how to get Lewis dot structures from condensed structures. So this is Chemistry 1110 that we're taking right now. Next semester, if you guys do well in this class and you want to go on for your bachelor's degree in nursing, then you'll need to take Chemistry 1120. Chemistry 1120 is all about organic chemistry, or the chemistry of organic molecules, which are carbon-based molecules. Well, carbon-based molecules can have many carbon atoms. Since carbon atoms can make 4 bonds, then we end up with multiple similar structures. So for example, I want to show you, if I give you the formula of C4H10O, and this is kind of a small organic molecule, then just having this, which is the molecular formula, that's not enough information to tell me what the structure looks like. I mean, up here, each of these little formulas, that's enough information to tell me what the structure looks like. I just follow the rules and I can build it. But 4 carbon atoms, 10 hydrogen atoms, 1 oxygen atom, it gets a little bit dodgy. There's more than one way that I can put it together that would be perfectly valid Lewis dot structures. So in fact, and this is in my lecture notes, I'm just going to copy and paste this figure. Here are 4 different structures. These aren't even the only ones, but these are 4 different structures that I can come up with for C4H10O. I can come up with at least 3 more, but let's just look at these 4. That's enough. So I want everybody to look at these for just a minute, verify that each of these has 4 carbon atoms. Each of these structures have 10 hydrogen atoms. Each of these structures has 1 oxygen atom. And if you want to, you can also verify that each of these structures has now used, then, let's see, 4 times 4 plus 10 times 1 plus 6, that's 16, 26, 32 electrons. You can verify that each of these has used 32 electrons. Just take a minute. Let me know when you've looked at all of those and you're satisfied that each of these Lewis dot structures really does fit that molecular formula. Oh, the plus 6 came from the oxygen, because I had 4 carbon atoms, they each came in with 4, 10 hydrogen atoms, they each came in with 1, and 1 oxygen atom, which came in with 6. They all have 32. Everybody, Meg says they look like they're all valid structures. No, it's fine. Yeah, it says O, oxygen. Now, next question is, are these the same compound or are they different compounds? I mean, have I just written the same thing 4 times, or are these really 4 different compounds I could get from this formula? They do all have similar structural features. Are they all connected in exactly the same way? They're not connected in the same way, but they do all have 4 carbons, 10 hydrogens, 1 oxygen, 32 electrons. Okay. Perfect. All right, so we all agree each of these is a valid Lewis dot structure for the formula given. So clearly, giving the formula is not enough information for us to know how these are put together. So when we get to organic chemistry, one of the tools that we're going to use is called a condensed structure. So rather than giving the molecular formula, if I can give a structure that's kind of condensed from this big bulky Lewis dot structure that might tell me something about the way things are connected, then that would be sufficient. So here's what we do with condensed structures. We take every carbon atom and we bundle it together with the hydrogen atoms that it's attached to. So we're going to bundle together this first group, that would be a C attached to 3 H's. Second group, here's a C attached to 2 hydrogens. And that's attached to another C, which has 2 hydrogens. And that third carbon is attached to another C, which has 2 hydrogens. And that C is attached to an oxygen, which owns 1 hydrogen. This is the condensed structure, or this Lewis dot structure. And I want you to see that we've placed everything in order of connectivity. This carbon is attached to that carbon is attached to that carbon is attached to that carbon, and that carbon is attached to that oxygen. And the hydrogens are placed on the atoms which own them. So this carbon owns these 3 hydrogens. This carbon owns those 2 hydrogens. This carbon owns those 2 hydrogen atoms. This carbon owns those 2 hydrogen atoms. And that oxygen owns that 1 hydrogen atom. Can you guys take a minute to look at that condensed structure and that Lewis dot structure and verify that it looks like they're trying to convey the same information? Danny, I'm not sure what your question is referring to. Oxygen comes in with 6 just because it was in group 6. So that's how we determine the total number of electrons. Here, the oxygen owns 8, so it's happy. It does have 2 lone pairs, but we don't have to state anywhere how many lone pairs something has necessarily unless we're in the full-on Lewis dot structure, which we usually put those in. But if I put O4, that would indicate 4 oxygens, and there's only 1 oxygen, so I wouldn't do that. Do you guys all at least feel comfortable with that? Those 2 structures, the condensed structure on the left corresponding to this Lewis dot structure right here, that these 2 are the same thing. So that's a simple example, but if you guys can at least see that, then that's the next step to seeing the rest of these. Okay. The next thing it would do, this is simple because they're all in a chain, sometimes they're branched. And if they're branched, then we'll often use parentheses to show that these are branches off of the same carbon atom, or it's branches within a chain. So instead of spelling these out for you, I'm going to put these down here. These condensed structures, let's see, we'll label them A, B, and C, correspond to these Lewis dot structures in no particular order. And I want you guys to look at these carefully and see if you can tell me which condensed structure is referring to which Lewis dot structure. Let's say if I label this 1, 2, and 3, you could tell me which is number 1. Is it A, B, and C, or C? Which is number 2? A, B, or C? Which is number 3? Take just a minute. Take your time. These are supposed to be semi-intuitive. You should be able to see those. Jay Houston says A is 2. Anybody else want to verify that? Confirm or deny? CME Lynn says yes. You guys are exactly right. A is 2. These two go together. Okay. So A is trying to say that this carbon atom owns 3 different CH3 groups, just like this carbon atom owns 3 different CH3 groups are all the same here. Okay, now I'm muddling it all up, so let me erase that. And then, in addition, it's also attached to this OH group, which, sure enough, it is. Beautiful. Well done. A is 2. All right. Here we go. Okay, Jay Houston says B is 3. What do you guys feel about that? Kylie agrees. Okay. So we're basically saying we've got a carbon atom attached to 2 of these CH3 groups, which then continues on the chain to be attached to a CH2, which is then attached to an OH. So here's a carbon atom, which is attached then to 2 different CH3 groups, here and here. And then this carbon atom is further attached to a CH2 right here, which is further attached to an OH. Perfect. That is exactly right on. Okay, so B then is 3. And then by process of elimination, it's looking like C is number 1. Does everybody feel comfortable with C being number 1? Well, sure. Okay. So what is this what do these parentheses mean then? Look at here at number 1. That it's a branch. Perfect, Robin. It's saying that this carbon is attached to the OH, but that OH does not continue my long chain. It's just a branch off of it. And so that CH is then still connected to a CH3 as a continuation of the longer chain. So what I have here is a CH3 attached to CH2. Here we go, CH3 attached to a CH2. This CH2 is attached to a CH, so the CH2 is attached to this CH. And this CH then is attached to an OH as a branch and to a CH3. So here's my OH as a branch and to a CH3. Did everybody follow my connectivity there? Erase all those little arrows so that you can see it a little bit more clearly, okay? These ones might be a little bit hard to see at first, but with a little bit of practice, I think you guys will get it, okay? They are pretty intuitive, right? You've got this long chain. All of the hydrogens belong to the carbon atoms listed before them. Each of the carbons are attached to each other in exactly the order given. So here we go. On your in-class activity sheet, this whole first page, section 4. If I give you some condensed structures, and these are pretty simple, not very, here's the only branch you even have. If you can tell me what the Lewis structure looks like. And I'm going to let you guys practice those on your own. I'm going to stop.